Welcome to your first lecture for ENGR B20 Programming and Problem Solving in MATLAB. This is Professor Steele talking to you, and let's get going. So the objectives of today's video lecture is to give you a brief overview of the course. I'm going to talk about the course objectives, what exactly are we hoping to get out of this course or to learn from this course. Then we will discuss course content, so how is the material going to be given to you, and then the structure of the course, just how is the course designed, and what's the flow over the next 16 weeks. After that, I will have a guest lecture come and talk to you and give you an overview of hardware and software on the computer. So basically, how does the computer, the hardware, the guts of the computer, which thinks in zeros and ones, digital code, how does that interact and talk to MATLAB, the program that we're going to be learning, or the software that we are used to using every day, and then kind of give you a flow chart of programming and how things overlap. Finally, at the very end, you'll get your first view of the MATLAB environment, just to introduce it on day one, and then future lectures will pick up from there. So our course objectives. Upon completion of this course, what are you going to need to be able to do? Demonstrate the ability to apply a top-down design methodology to develop computer algorithms. Now you'll notice that this doesn't say MATLAB in it at all. These are general techniques. You're going to learn general techniques to write better code, or just to basically problem solve and use coding as a new tool in your problem solving toolbox. The things that you'll learn from this course will make you a better problem solver in general and should be applied to any engineering course. For example, to design your code, you're going to have to be thinking about the, what you know about a problem, or the inputs in programming, and then what are you trying to come up with, or what's the solution you're looking for, and that would be the outputs of a computer program. So we will discuss, and you'll learn a lot more about the top-down design methodology, which applies in a lot of different environments. From there, you're going to need to create, test, and debug MATLAB programs. Now, initially, we're going to learn linear programs, top-down programs that start with code in line 1 and move to line 2, and so forth. But then towards the end of the course, we're going to learn a different style of programming called object-oriented programming, and then from there, if you want to take in more advanced programming classes, you can. Throughout the course, we're going to be talking about numeric techniques and computer simulations, for particularly how they apply to or can be used to solve engineering problems. So how can we solve the problems that you're going to be learning all about in other courses? How can we use MATLAB as another tool to help us solve those? And how can we make general code to apply to those kind of problems? And then finally, we just want to make sure that you're able to use MATLAB and a lot of the resources and built-in functions and capabilities. As we get going, you'll learn that MATLAB is just this enormous program, and we will barely scratch the surface of what it can actually do. And you can hopefully take this class as a starting point. You'll learn the syntax and how to correctly comment on code, so that you can take a look at data for future projects. And finally, one of the last things we're going to talk about that goes kind of with the object-oriented programming is how to use data structures to efficiently handle data in MATLAB. All right. So now that we kind of know, what are we going to be learning and what's the order that we're going to be learning it in, what are the resources that we have now? How are you going to be learning the material in the course? So there are basically 3 resources that the course is structured around. The first is your textbook and reading handouts. So you will need to make sure that you keep up on reading the textbook, plus any other additional handouts that I post to Canvas. These will be put into the modules each week for you to read before our meeting on Thursdays. You want to make sure you are reading all of the assigned readings prior to our face-to-face portion of the course. But I would encourage you that as you're reading these materials, read them next to a computer with MATLAB open, so that as you're reading about particular functions, you can actually stop, or commands, you can actually stop and test out the things you're reading about. I'm just reading about coding is incredibly boring, and you'll just to stay awake, you might need to pause and test the things out. But that's also part of how you learn coding is time on program. So the more you're in MATLAB and doing the commands and using the commands, there is a little bit of muscle memory, if you will, of your hands learning the program for your brain. Okay, so that's the first thing. The second is what you're currently doing. These video lessons, for these ones, you're going to need to watch the entire thing. I apologize, some of them are going to be quite long, like this one is probably going to be an hour-long video lesson. But for coding, I can't really break them up into much smaller chunks. So these are the lectures that you would typically go and sit into a classroom and listen to the instructor lecture for an hour. I've posted these now as video lessons. So I encourage you to, just like if you were in a lecture course, listen attentively and take notes. There have been studies that show the act of writing something down, connecting different parts of your brain, the parts of your brain that control the motion of the writing, and as well as connecting to what you're hearing and turning it into written word, that makes you actually learn a lot better than if you just listen strictly alone or watch the videos alone. So just like if you were in class, take notes down, write down anything that's not clear so that you can ask them either through email, ask those questions either through email or when we meet face-to-face for that portion of the course. And then again, just like when you're reading, take advantage of the fact that you can pause the video and code alongside it. I wouldn't recommend trying to code while watching the video. That will kind of get rid of the whole first bullet point there of listening attentively. I want you to make sure you're listening to the video. Pause it when you get to an area. You can still see the code on the screen, and then go into MATLAB and do your own code. But take advantage of the fact that you can watch the video, pause it, code, go back and relook at anything that you might have missed or didn't do perfectly in your own code. So don't just watch the videos, but actively watch the videos. And then finally, what is your output for the course? And that's going to be labs and homeworks. You will need to be doing those. And the advantage here is as you're doing the labs, if you get stuck on something or you remember that I talked about a particular topic as you're working on the lab or the homework, but you can't quite remember, well, you can always go back to the video lessons and re-look at that material. So that's a huge benefit to the structure of this course being hybrid, is that you'll have access to all of those video lessons while you're working on your labs and your homeworks. So make sure that you're using them to your advantage. And as I'm talking about the labs and homework, make sure you're doing it. Now, if you look at the schedule of the course and the syllabus, we have a very ambitious schedule. We are covering a ton of topics. And if you fall behind early, it will be very, very difficult to get yourself caught back up. So make sure you're doing the homework, do it on time. There will be due dates. If you're reading the syllabus, you can turn in homework late, up to a week after it's due, for some partial credit. But you don't want to be stacking homework on top of homework. So just try and keep up, stay on time, make the time to do your work and get it turned in on time. And one major way that you can help yourself help yourself get those labs and homeworks done on time is to not go straight into MATLAB for every single assignment. You should be stopping and doing some develop the logic or the thinking that's going to go behind the lab or the solutions to the labs prior to your actual coding. And we'll talk about that pseudocoding and top-down methodology in a lot more detail later. So I will, once we get to some of the more difficult labs that are going to be a little more time-consuming or that really need this kind of logic and planning, I will have you turn those in prior to course, just your handwritten notes or your plan of attack. I will have you upload those to Canvas just to make sure that you're getting A, some credit for doing that work, and B, so you're making sure to get it done. And then finally, the last step would be to program in MATLAB, which sounds simple, but as we go along, you'll find that a lot of times there will be errors that we have to debug, and maybe you'll have to think about making your code a little more efficient or more general than the first time you ran through. So there's a little bit of repeatability there as well. Again, for this course, all the resources are going to be on Canvas. Already up should be the syllabus, as well as a list of the detailed learning objectives on what you're supposed to be being able to do, including some of the more common function commands or commands that you'll be learning at various times. So you can kind of look over that list of learning objectives and make sure that you are capable of doing what you need to be capable of doing as the semester moves on. You can also find their textbooks information, as well as in the syllabus our day-to-day schedule for topics and assignments. So you can look over that entire list, and there will be documents and readings posted on Canvas. In the syllabus, you can also find the course requirements, the list of the learning objectives that we already went over, the grading policies. So make sure you take a minute and read through everything in the syllabus. And then the online in Canvas is also where you're going to be finding the readings, the labs, and the homework documents, which you'll need to download the Word file, make changes to, and submit your solutions, and then resubmit onto Canvas. So Canvas is going to be incredibly important to you. You should be checking it and your Bakersfield College email daily, just to make sure you're staying up with everything. All right, so just a little more information on the video lectures in this course. Many of the materials that you're going to be using have been pulled from outside sources. For the majority of especially the video lectures, this is material that was developed by other community colleges here in California in the CalSTEP program. They have funding from the National Science Foundation, so they had federal money available to help them build a set of online course materials for other community colleges to use, particularly for community colleges that might not have enough students to fill a course every semester. We could still offer courses online in that situation. So last summer, I actually attended a conference on how to use that material effectively, as well as they provided me with the laptop and all the software I'm using to create these videos for the hybrid portion of this course. So let's actually take a minute and look at a little bit of information on their website. So here is the Kenyatta College website and more information on the CalSTEP program itself. So you can see at the very bottom here, they talk about the materials based on work from the NSF and the grant. So they had that federal funding to develop all of this stuff and make sure, if you look here, one of their goals was to train engineering faculty, such as myself, to use this curriculum and give community college engineering transfer programs these engineering courses. So I did want to look at the team that was involved here. The lead here, Amelito Enriquez, Eric Dunmeyer, and Tom Riewald, who put in just an incredible amount of time. Nick Langoff, Tracy Huang, and the top three here are the main people. And the name that you might be most interested in is Eric Dunmeyer. He is actually the one whose voice you're going to be hearing in just a few minutes, because he put together all of the MATLAB videos that I'm going to be pulling quite a bit from. So he'll be coming in to talk about the hardware and software and you'll hear a lot from Eric Dunmeyer and the videos that he's created for covering MATLAB throughout the semester. So without further ado, let's hear from Eric Dunmeyer.
I also wanted to take this opportunity to give a very brief overview of hardware, computer hardware and software itself. Talk a little bit about the layout of a computer, how it interfaces with software, and where MATLAB fits into this grand picture. And so I think it's important that we all have the same sort of basic understanding of these things before we start the course. So first I should ask, what is hardware? And of course, hardware is actual physical objects associated with the computer. Software, on the other hand, is something that you can't really touch, but is rather the data and or instructions that interact with that hardware. So what is it that we would like the computer to do? And one of the role of computer engineers is to understand that interface between software and hardware on a very detailed level to make sure that they understand how the design and layout of the hardware interacts with the capabilities of the instructions and the data, the software that we'd like to execute. In terms of the layout of the hardware, virtually all computers today follow this standard computer architecture organization, often known as the von Neumann architecture. And it has this central processing unit or microprocessor that is sort of the core brain of the computer that's composed of essentially two subunits. What is known as the ALU, or Arithmetic and Logic Unit, that does a lot of the comparisons and operations that we'd like to perform in the computer, and the control unit that is in charge of transferring information from one place to another, sequences of operations. We also have interfacing with this CPU a number of other important components. One is a collection of various input devices that we might have for getting information into the microprocessor, and various output devices for getting the information back to the user. We also have different types of memory. There are certain types of memory that are built in to the computer itself, what we might call internal memory for storing information. And we also have various external memory devices that are either peripheral or associated with the computer in some way. And so we'll talk about each of these in a little more detail. So first let's talk a little bit about input and output devices. Of course, there are many common input and output devices, and these are growing on a yearly or perhaps daily basis in terms of the variety of input and output devices that are available. And so a few of those are pictured here. And if my pen begins working, some common input devices might be things like a microphone for sound, a scanner or camera for images, a keyboard and a mouse, which we've left off on this one. For inputting various numbers, text, clicking on things in graphical user interfaces. And of course, I've half-circled the monitor here because in many modern computer devices, the monitor itself has now become a touchscreen input device. We also have a variety of different common output devices, and some of those are pictured here. Things like the monitor itself for displaying visual output, speakers for outputting sound information, printers for creating hard copies of information, headphones as an alternative to speakers for sound, of course, one that you may use if, for example, you're sitting in the computer lab watching and listening to one of the video lessons. So all of these are various output devices, and there are, of course, many more, as I mentioned, that are added on a daily basis to our options. In terms of the processing and memory that we mentioned, we have this microprocessor, which is sort of the brain of the computer, that is actually doing most of the hard work of thinking and computing. And then, as I mentioned before, various types of memory that are associated with the computer. One important type of memory is the read-only memory, or ROM, that in some sense is almost like the deep core part of our brain stem, that essentially stores very vital data and instructions for the sort of fundamental crucial tasks. Just as our brain stem in our body is responsible for things like breathing and heartbeat, the ROM in the computer is responsible for those basic boot up functions when you first turn on and turn off the computer, to make sure that the information is available there to start the computer up, get the operating system running. What is sometimes called the BIOS system, or some alternatives to that these days. Also, another type of memory that we have in the computer built in is our RAM, or random access memory. And this is the place where we are temporarily storing information while we are running various applications or programs on our computer. And so information is constantly going in and out of our RAM. And as we'll see, as we write more and more complicated computer programs, we can begin to use up significant amounts of that random access memory, to the point where we can actually use up all of the RAM and cause a computer crash. And we'll talk more about that idea later. And of course, in addition to these built-in types of memory, there's often usually a hard drive on your computer, more like a closet or dresser, if you will, for keeping things, storing information. And so on your hard drive, you store a lot of the various types of files and information data that you use on a regular basis. And in addition, we have removable types of memory. Many computers still have either a CD-ROM or DVD-ROM drive, although fewer and fewer of our modern computers have this anymore. Floppy disks was the traditional way of storing information for portable storage, but hardly found anymore on modern computers. And nowadays, more and more, we've tended to use other types of portable memory, such as a flash memory stick that we might stick into the USB port on our computer for taking information with us, moving it from one computer to another, and of course these days more and more storing information in the cloud, or in other words, storing information on somebody else's computer somewhere else, right, by taking advantage of our internet connections. And so all of these are important ways for storing information for computers, and you will, of course, and probably already have, used many of these types of memory in the past. So in addition to this sort of big picture view of computers and their layout and hardware, it's worth taking a moment to talk a little bit about the detailed view, because it helps us to understand the interface between the hardware and the software. And what I mean by the detailed view is the idea that inside the microprocessor and these various types of memory, built-in hard memory, are transistors. And transistors are integrated circuit switches, if you will, that are microscopic electronic devices that can exist in essentially one of two positions: an on position, which we often represent in the computer world by the number 1, or an off position that we often represent with a 0. And so we often talk about the fact that computers are binary, and that means simply that there are two different possible states, on or off, represented by 1 or 0, for these different transistor switches. And of course, one of the things that computer engineers have been quite adept at over the last couple decades is making these integrated arrays of transistors smaller and smaller so that we can pack more and more of them into smaller and smaller spaces. So we now are able to pack literally trillions of these things on a relatively small device. So how do we use these transistors in order to represent information? Well, it turns out that the way a transistor works is with a relatively small electrical signal voltage, we can flip the switch, so to speak, on any given transistor between the on or off state. And so we can then use a bank of these transistors. For example, in this picture, we see 8 of these transistor switches that can be arranged in some particular set of on and off states. So you notice with this particular set, we've got almost all of them turned off, except for the second and the last switch in the on position, giving us a 0, 1, 0, 0, 0, 0, 0, 1 code, if you will, set of switches, which can then be used to represent some particular piece of information. For example, the letter capital A. Now, if you can get a large number of people to agree on what that standard representation for the capital letter A is, we now have a simple way to communicate with each other and communicate with the computer in a standard way by having a capital letter A always represented by this particular set of switches. And in fact, these types of conventions have been established for computers. One of the common conventions is known as the ASCII code, ASCII, which is one agreed upon international convention for representing certain types of text information on computers using a set of 8 of these zeros and ones, which are known as bits. And so we often talk about an 8-bit representation of certain types of characters. And I should note that 8 bits corresponds to what is sometimes known as 1 byte of information. So 8 bits represents 1 byte. This is sort of a convention that went back historically in the early days of computers for how information was represented. And so nowadays we often talk about the number of bytes of memory that are required. And you may note that using the SI or metric style system of representation, 1,000 bytes would also be known as a kilobyte. 1,000 kilobytes is a megabyte. 1,000 megabytes is a gigabyte. And of course, 1,000 gigabytes is 1 terabyte. And just simply going through those different powers of 10 reiterates the tremendous increase in memory capability that computers have undergone over the past few decades. Once upon a time, it was not unheard of to buy computers that had a megabyte or less of memory associated with them. And nowadays, we're talking about terabyte-size hard drives when we buy a computer. And so there's really been an order of magnitude increase in the amount of memory that we can store, and therefore the amount of data, letters and numbers and so forth. As we go through our discussion of representation of data in the MATLAB course, we'll talk about the idea that although we do sometimes use various types of 8-bit data representation, more often we will use a larger number of bits these days to represent things like real numbers. And so it's not uncommon, in fact our default numerical representation involves 64 bits, or in other words 8 bytes of memory, in order to represent our default double data type, as it's often known, floating point double precision number. But when we need to save memory for certain applications where we might have extremely large amounts of data, we might switch to an 8-bit representation or 1-byte representation for certain types of data in order to save memory. And we'll see an example of that this semester when we talk about working with large image files. Next, I wanted to talk a little bit about software hierarchy and where MATLAB fits in the grand picture of software. So we've now understood that the basic layout for the computer hardware, and we understand that interface between hardware and software at the most fundamental level, this idea of translating these little microscopic switches into zeros and ones, which can then be used to represent letters and numbers. We then move out from there into various layers of software, or in other words, data and instructions, that works with these voltage pulses and zeros and ones in order to perform computations and actions and execute a list of instructions or sequence of instructions. And so layered around the hardware, if you will, is the first layer of software that we often call the operating system. And of course, there are a variety of operating systems out there. The one running on this computer at the moment is the Windows 7 operating system. But of course, there are new versions of the Windows operating system all the time. And of course, we know that Apple has its own operating systems for some of its devices. And as the variety of devices expands from sort of personal computer desktop devices to various types of mobile devices, the number of operating systems also seems to be increasing. And that becomes important because as we then develop the next layer of software that we often call applications, things like Microsoft PowerPoint or Excel or MATLAB itself, these applications need to interact through the operating system with the hardware, and so we need to make sure that those applications are designed compatibly with the operating system on a particular device. And then, of course, the final outer layer of this structure is the users themselves, which might be yourself or someone else who might use your computer program that you've designed in the future. And so we need to think about how do users interface with these software applications that in turn need to interface with the operating system and the hardware. And so we'll talk a lot throughout the course in making sure that we understand this interaction between users and applications and operating systems as we go along. In terms of writing computer programs, we could start at the simplest level in what is sometimes called machine language or first-generation language. That is, in essence, those zeros and ones themselves that communicate with the hardware of the machine. But of course, it would be incredibly tedious to have to write a set of instructions in order to do any significant task if you had to type all those zeros and ones yourself in order to represent various letters and numbers. So instead, we create various types of higher level languages that we might call second generation or third generation languages. And one of those is known as assembly language. And assembly language is essentially a language that is very simplistic, what we might call a very low-level language, which means that we need a large number of instructions in order to accomplish a relatively simple task. And assembly language was once upon a time often used with controlling various instrumentation and devices. And it still can be used today with controlling, for example, robotics and things like that. If you need very precise control of devices, instrumentation, assembly language provides fairly limited capabilities, but very precise control. And an analogy might be if you wanted to explain or tell a robot to go to the store and get milk, you would need an assembly language to provide very detailed instructions that might start with something like rotate 90 degrees left, shift weight to the right leg, move left leg 6 inches forward, shift weight to the left leg, and so forth and so on. And you could imagine that it would take quite a few instructions in order to get this robot eventually to the store in order to be able to buy milk. Whereas we'd like to be a little more efficient in our programming, we can move to a higher level programming language. And so the third generation programming languages that came after this were things like Fortran, BASIC, C, and so forth and so on. And these allowed programmers with much fewer sets of commands in order to invoke more complicated actions. So in our analogy of going to the store to get milk, with a third generation language, you might be able to simplify your set of instructions to say something like exit the room, turn left, exit the building, turn right, follow the sidewalk, and so forth and so on, in order to get to the store to buy milk. And so you don't need to offer quite as much precise control, in this case, of how each of these actions is going to be done, because you're essentially using a subprogram or subroutine, if you will, that by simply typing a simple set of commands will behind the scenes execute a much larger number of operations within the computer. More recently, even higher generation languages have been developed, and these require much fewer set of commands, a much smaller set of commands, in order to accomplish fairly complex tasks. So in our milk analogy, we might simply be able to tell our robot, go to the store, buy milk, and perhaps those two commands might be sufficient if somebody had already pre-described a default set of tasks that went along with each of those in order to get the robot to the store successfully. And so really here we're looking at some much higher level programming languages. Some of those that you may be familiar with are things like C++, Java, Python, what we will call object-oriented programming languages that are intended to do fairly high-level tasks with a moderate number of instructions. And even perhaps higher than those are these software environments, such as MATLAB, Mathematica, MathCAD, Maple, that are not just programming languages, but really entire software environments that one uses that have built-in very high-level tasks that can be executed with a very small set of instructions. And we'll see throughout the course in MATLAB that sometimes we can do some rather fascinating things with just a few commands. And I'll demonstrate one of those shortly. Some of the graphical capabilities, for example, in MATLAB. Simply by typing the command plot, x comma y, we can generate a fairly sophisticated graph. And behind the scenes, a number of default actions have taken place that generate axes with certain font sizes and axis limits, line widths, background colors, and so forth and so on, that do not necessarily need to be specified if one doesn't want to take the time to do so. But you still have some of those lower level capabilities of tailoring the program however you like, or the plot however you like, if that's desired. And so we'll see that MATLAB is a quite high-level programming environment. One additional thing worth mentioning here in this overview of MATLAB and programming is how MATLAB differs from some of the other more conventional programming languages. In fact, MATLAB is sometimes called a scripting language rather than a programming language because it is what we call an interpreted language. So first we should describe what is the more traditional way of executing or compiling a program. And so if we were in another language such as Fortran or C++, what we would first do after writing our computer program in quote-unquote human language, that is in our programming language, we would need to compile that program in order to translate it into what is often known as object code. That is to translate it from that higher level set of instructions to a much lower level set of instructions that can be better understood by the machine. But in the process of translating those high-level instructions to the low-level instructions, sometimes we make mistakes, what we often call syntax errors, bugs, in our computer program that make it impossible for the computer to compile the program, or in other words, to translate it. And these you might think along the lines of what you might consider grammatical errors and spelling mistakes, if you will. You've typed a particular command the wrong way, you've spelled it incorrectly, or you've put it in the wrong order. In other words, you've used the wrong grammar. During the compile process, the computer will kick that out and tell you that there's an error. And so you'll need to return to the programming stage in order to fix any of your errors, or what we call debug your program, and then compile it again until it compiles successfully. Once you've successfully compiled the object code, the next stage is to do what's called linking, in which that particular program that you wrote is linked to some other programs that might be required to support it inside the microprocessor. And once that's completed, it produces what is known as an executable file, which can then be executed or run from the operating system. During that execution, you may have designed your program so that it requires some sort of input, whether from a device or from the user. And so it pauses in order to collect that input and ideally produces some output. But often, once again, during the stage of execution, it either may stop running due to some sort of error that's created during execution, or it may simply produce output that is not correct. In either case, this is due to what we often call logic errors. That is, we've used the right spelling and the right grammar in order to write our code, but because of the instructions that we gave, we did not get the result that we desired. There was some error in the logic of how we wrote our instructions. And so once again, we need to return to the programming stage. It's often more difficult sometimes to debug such logic errors, try to figure out what's going wrong with the sequence of instructions or algorithm that we've designed, fix that, and repeat the process over again. So this particular layout that I have on the screen is sort of the traditional programming approach that one might do in Fortran or C++ or C. However, in MATLAB, there's a very different sequence of events that takes place. Instead of having to write the entire computer program first and then go through each of these steps sequentially, MATLAB actually does the compiling, linking, and executing all at once every time you write a line of code and hit enter. And so for this reason, MATLAB is described as an interpreted language. Each line that's typed by the programmer is interpreted, compiled, linked, and executed in order to create output if such is desired. And we'll see as we go through this course, this style of computer programming or scripting has its advantages and its disadvantages in terms of generating and designing software. So we'll see some of the advantages and some of the disadvantages as we go along in the course. But I find that, in fact, having an interpreted languages can be very helpful in introductory programming because it allows you to experiment, if you will, and see what works and what doesn't work as you're designing the program. You can explore how certain statements work and how variations on those statements will produce variations in the output. So that hopefully has provided you with sort of a general overview of both what we're going to accomplish in the course and also an overview of how MATLAB operates and how computers operate. What I'd like to do now is just briefly open up MATLAB and take a quick look at it. And as I mentioned, you're going to follow up by doing some more detailed hands-on exercises on your own. So first we need to start the MATLAB software, and depending on where it's installed on your particular computer, you can usually find it under the program list, or you may have a shortcut on your desktop or in a folder in which you can start the MATLAB program. And one thing I should mention, as it's booting up, it usually takes a little time on most computers in order for MATLAB to fully open, so be patient. And of course, MATLAB, because it's a software package or application, it is revised on a regular basis. That is, there are new versions. And so the one that's opening here, we can see is the 2014A version. And there's already a newer version out, a 2015 version. And so you should expect that as new versions come out, they will be slightly different than previous versions. Most of the previous capabilities are retained from one version to the next, but new capabilities are added. And on occasion, there's even a noticeable change in the layout of the desktop environment. But for the most part, once you learn how to use MATLAB, you should be pretty safe to be able to continue to be able to use it efficiently, even over many different version iterations. Once MATLAB does open up, you'll notice that there are a number of standard windows, and we can see those here. So we have, in the current version, a header ribbon across the top with a variety of different tools available. Down below, we see one important line which indicates our current directory in this box. And by going over to the icon that allows us to browse for a folder, if we click on that, we get an interactive dialog box that allows us to browse to any folder on the computer as you normally would in most operating system environments. And so we can choose a particular folder as the folder we like to be our current directory and select that folder. And we'll see later that this is important when we get to writing script files or programs and saving them, or if we want to access files, they all need to be in the current directory that you're working with. And you may decide that you want to change that current directory on occasion. For example, if you'd like to organize all of your files by assignment number or so forth, you can create separate folders for each of those and then simply change the current directory to the folder that you're currently working on for that assignment. Once you've selected a current directory, you will see its contents listed in the current folder window that we see to the left here. And so this current folder has quite a few different files listed in it. You'll notice that most of those are .m files or mat files, which MATLAB uses, and we'll see that these will be the common file types that we'll use when we're writing scripts, when we're writing functions, and so forth. But we may also have other files that we'll read from or write to, such as text files and image files, such as JPEG files, and so forth. One of the most important windows that we see at the current moment is the central window that's known as the command window. And the command window is where we can type various commands in MATLAB. And at the beginning, we'll tend to do a lot of our exercises at the command window so that we can get comfortable using it. And in a lot of ways, the command window works almost like a calculator in that we can type various commands and execute them by hitting the Enter key. So for example, if I just want to type 5 plus 2, I can do so, hit the Enter key, and that causes an action to take place, and you'll notice that MATLAB simply calculated 5 plus 2 and got 7. And you'll notice that it put that output in a rather odd way. It said ANS equals 7. And what MATLAB has done here is actually created a default variable, which it always calls ANS. So if we don't specify a variable, that is a word, in order to represent the place where we're storing the result, MATLAB will store it in this place that it calls ANS, this variable. And you'll notice that down in the bottom left window, which we call the workspace window, the word ANS appears with a little icon, and the value 7 appears next to it. And so the workspace window reflects all of the variables that we have created thus far in our session, and if possible, displays what their current values are. And so, as we'll discuss later in the course, we can create our own variable names. I might create the variable x, for example, and say x equals 5 plus 4, and hit Enter. And now not only does MATLAB execute that statement to add 5 and 4 to get 9, it also stores it in this variable x so that I can use that variable later on for other computations. So for example, if I then wanted to take x plus 3, and hit Enter, MATLAB will now take the stored contents of the variable x, which was 9, add 3 to it, and compute the result to get 12. And since I did not tell it where to put that result, it put it in the default variable ANS. And you'll notice that in the workspace window, it has changed the value from 7 to 12 because it stored the new result in ANS and erased the old one. Another window that you'll notice here is the command history window that's over on the right side. And this simply keeps track of all of the commands that we have typed up to the present time, cataloged by date and time of the beginning of the session. And you can make use of that on occasion if you'd like to go back and recover, for example, some of the commands that you've previously typed and rerun those. You can simply copy and paste those commands at the command prompt and hit Enter again and re-execute all of those commands once again. So that's one convenient way to rerun various commands. Another thing that you'll play around with in your orientation exercises is the idea that in MATLAB, by using the up and down arrow keys, I can actually toggle through all the previous commands that I've typed as another way, as a shortcut to get back to a previous command and execute it again. All of these are convenient tools in MATLAB. On occasion, we may not want to have all of these windows open. We may want to, for example, hide our command history window so that we can make our command window larger. And so if we would like to do that, the little drop-down arrows on the top right give us various options. And we'll notice that some of those options include minimize, maximize, undock, and close. If we'd simply like to undock the command history window, we can do so, and it's now essentially still there. It's just hidden in some layer behind the scenes, and we can pull those windows out again at any time if we'd like to. For example, you can go up to the buttons along the top, and there's a Windows option there where we can pull up the command history window again if we like, and from the drop-down menu, dock it back into our workspace, into our environment. One command or a couple of commands that are going to be particularly useful to you are the clear command and the CLC command. The clear command simply clears all of the variables that are in the workspace. That is, it deletes them and their contents and gets rid of them. The CLC command, which is short for clear command window, essentially clears that, erases that central command window screen so that it puts your cursor back at the top. And one of the things that I should note here is that the command window has this symbol that looks like a double greater than sign, and this is known as the command prompt, and it simply indicates where the current input location is for typing commands. And so every time you type a command, you'll get a new command prompt when it's ready to receive another command from you. And this particular command prompt has the word trial in front of it because this happens to be a trial version of the software. If you have an educational student version of the software, yours will say EDU for educational in front of the command prompt. Another thing that's a very useful window that we'll explore later is the editor window when we get to actual typing of programs. And we can access that editor window in a couple of different ways. One way is by simply clicking the blank script or new script button in the top left, which will open up the editor window, and it's opened up for us a blank editor window where we can type various commands and save them in a file so that we can reuse them later. And early on in the course, we'll use this editor window as largely a scratch pad, if you will, to copy and paste commands from the editor window into the command window to play around with them. But we will eventually reach the point where we can save, for example, a whole set of commands in a program in order to execute them later. And we'll see plenty of examples of this. And I mentioned earlier that couple of the important capabilities of MATLAB revolve around both arrays and graphics. So for example, one thing that you can do in MATLAB that's fairly powerful is with a small number of commands generate a whole set of numbers. So for example, I might create the set of numbers that goes from 1 to 20, let's say. And I'll display them in a way that's vertical rather than horizontal so they fit better. And so we see here with a fairly small number of commands or a very small amount of typing generated the list of numbers from 1 to 20 and stored them in the variable x. And then I can quite easily perform some operation on those numbers. So let's say I wanted to square all of those numbers. And the caret symbol is the one that's used for doing powers in MATLAB. And as we'll learn later, doing dot caret 2 allows us to calculate the second power of a whole list of numbers or array of numbers. And so now I've calculated the squares of all those numbers and I've stored them in the variable y. And then in MATLAB I can simply type the commands plot x comma y and hit enter. And MATLAB will generate for me a graph of y on the vertical axis versus x on the horizontal axis. And it will use various default decisions about what size fonts to use and what axis limits to use, what colors to use, and so forth and so on. And so one of the nice, powerful things about MATLAB in terms of graphics and programming is if I've already written a script, such as the one here, that indicates a series of commands that affect the format of that plot, I can simply run that run that script or program in order to enact all of those various settings. And so one way you can run a script in MATLAB is by just clicking the Run triangle button, or alternatively you can type the name of the script at the command prompt. Either way works fine, and I'm going to shrink that window a little bit so that I can get both of my windows visible at the same point in time here. And so we'll notice that if I hit the Run command, I'm prompted at the command window for a desired plot title, which I programmed into my script. And so maybe I'll type some plot title like demo plot and an X and a Y axis label, and I'll just call the X axis X and the Y axis Y. And now if we go pull up our plot or figure window, we can see that all of the formats have been changed so that the font size is larger, and we have title and axis labels. The color of the curve changed from blue to red, and with a thicker line on it. We have grid lines, so forth and so on. And so one very powerful thing that you'll learn to do, especially later in the course, is to control the details of formatting of various built-in types of graphics in MATLAB to your own customized desires. And so that's a very powerful capability within MATLAB. And one other thing that's worth demonstrating in this lesson is some of the really powerful graphing capabilities in MATLAB. So for example, now that I've cleared my commands window and cleared the workspace, I can type a fairly simple set of commands, such as the following, X, Y, and we won't worry too much at this stage what these commands are doing. You'll learn later what all of these commands are. But essentially here I'm generating two arrays of numbers simultaneously and storing them in variables X and Y. And I'm suppressing output using the semicolon at the end of the line so that it doesn't all echo out onto the screen. And then next I'm going to simply make a mathematical calculation here where I'm going to take the square root of the sum of the squares of those numbers and then just add on a tiny bit more, epsilon, a built-in function in MATLAB. And then finally, I'm going to take those values and take the sign of those values and divide them by the values themselves and store them in the variable z. And finally, I'm going to create what's known as a mesh plot of the variable z. And my figure window is hidden, so I'll need to pull that up front. And we see that in doing this rather brief set of 4 commands, I've generated a quite beautiful graph of what is sometimes known as the Mexican hat shape in MATLAB, which is often used in a lot of their advertising and marketing materials. And one useful tool is to be able to click on the Rotate 3D tool in MATLAB and then click on the graph, and then you'll be able to rotate the view of this graph around. A little hang up on my computer here. There we go. And to be able to look at this from various angles, And we can see that we've, in fact, created a true three-dimensional graph of these variables, really of the variable z. And so this three-dimensional graphing capability in MATLAB is one very nice and powerful capability that you will take advantage of on occasion in various science and engineering applications. And I just wanted to briefly demonstrate how simple it is in MATLAB to generate such plots and control them. And as I mentioned, during the orientation exercises that you have for this opening lab, you'll get to play around with some of these commands yourself and these windows and create that Mexican hat yourself. And as we move on in the course, you'll of course learn how to do such things in a great deal more detail and understand how these commands work and how these arrays work. So that is it for this current opening orientation lecture. And I look forward to a good semester of learning with you in the course, and I'd like to welcome you.